All right, today's been a long day for me. A lot of different meetings, and then having the babies here. Definitely, we'll see how well this goes. So let's see here. The past two times we've been talking about linear regression. We'll kind of continue that, and it's going to be again a little more freeform. Hopefully, you guys are getting close to catching up on the material. On Friday, we'll actually be launching the phase 2 project. So if you actually paying close attention on Canvas, it's actually up on Canvas right now. So if you really want to, you can kind of check it out. Look what that looks like. But we'll talk about it on Friday in detail, like what it looks like and what the expectations are. In short, it's going to be focused around linear regression. And basically your job is to, your goal is to develop a linear regression model that best predicts the house prices for, I think it's not the Ames data set, but a data set on like different features of the house. So that's kind of what's coming up, which is actually kind of cool because today we're going to kind of walk through a Kaggle competition that we'll launch, and it's got the same feel for there. Of course, the Kaggle competition is more for fun, so like it's completely optional. Though I do, suggest everyone try at least once, do a submission just to get a feel for it. I think it's kind of a fun way to kind of see a little bit what we're doing, and we'll walk through that later today too. Okay. But before we get started, is there any like overall like burning questions that you guys might have from earlier this week? No questions? Cool. All right, so let me just go ahead and get my screen going here and share. I'll make sure I'm hitting the right one. Yes, okay. So I think you all can see the Jupyter notebook, like list of little notebooks and stuff like that. Yeah, perfect. Thank you for the thumbs up. All right, so we talked about a whole bunch of things like these past couple of days. We introduced linear regression, simple and multiple linear regression. Hopefully we got a pretty good feel like what that does. We spent a good amount of time yesterday going over like categorical variables, which can be pretty tricky, I think. And we kind of went through those details a little bit. But in short, with categorical variables, once you identify that they are a category, the big thing is that you probably would want to one-hot encode them, which is a typical like method that we would use, which is basically, if you remember, if you can use like the get dummies. There's also a one-hot encoder built into sklearn. So we'll kind of maybe show you guys a little bit of that today. So mostly today is going to be focusing on like, okay, we got linear regression. What other improvements can we do? And then actually trying to like do a little walkthrough of like what that process looks like when we actually go through feeding in data, doing cross-validation, developing our model, and hopefully getting good results. Okay. So let's see here. I think what we'll talk about first. I think we'll just kind of, I don't think we talked about multicollinearity directly, but yeah, let's talk about this really briefly. So I brought up a couple things that can happen with multicollinearity. And so one of them yesterday was about with get dummies, right? You would get, if you had 3 categories, we'd have category 1, category 2, category 3, and we have to drop one of those, right? And the reason I kind of gave behind that is that because those categories can be, it's only one of them and not the other one, like the other categories, it kind of implies if you know all the categories except for the last one, then something about that last one. So it kind of double counts that information. And that can be really problematic because basically that means that we now have a feature that's correlated with other features. And on a small level, that's okay. But if that becomes like, becomes a main focus of the model, we can actually have some really weird stuff, or we have large changes in the prediction model from small changes. So you can kind of imagine is that like the coefficients kind of, I like to think of like eat up or kind of share too much of those values across each other. And so basically if you're double counting them, the model doesn't know which value, which feature should have more importance. So it's a toss up of like what exactly the model will determine. Like the model is deterministic of like what's the best model, but depending on what the data is fed in, it might put a lot of value up on feature 1, or it might put a lot of value on feature 2, or might split the values between feature 1 and feature 2 because feature 1 and feature 2 are correlated with each other. Okay. Does that make sense to people? At least the concept. Okay, so we want to avoid that. So one thing that we can do is essentially just make sure that we address those things early on, kind of identify them. And I think the biggest, most obvious one, oops, why don't I have Seaborn? Oh, this is what happens when you don't launch your, sorry, everyone, I gotta restart my Jupyter notebook. I didn't activate my learning environment today. Let's try that again. Okay. There we go. All right, cool. So like we saw like with the automotive and stuff like that. In this case, you know, we can look a little bit at the scatter matrix before seeing like what things are categories, and then actually checking out a little bit of correlation. Like we kind of mentioned, I think it was Safe had mentioned like displacement and like horsepower and weight were very similar to each other. And the big thing we want to avoid is anything that's directly correlated with each other, because it's basically double counting information. Now, in a lot of ways, like I'm going to tell you is that one solution, like we saw with Get Dummies, is you literally drop one of the category or one of the features, one of the columns. I kind of like to think of this is like the machete way of like just like chopping off, you know, fixing the problem, where I will tell you later on we'll find better solutions. And one of those solutions is something called principal component analysis, or PCA. And so that's something we'll see more of advanced machine learning techniques. But for now, like for the most part, you can kind of think it's like, you know, if there's a lot of correlation between the features, you might want to consider dropping it. Or what you can even do, since you're going to make multiple models and see how well they do with cross-validation, you can kind of make the model with those features involved. Let's say, for example, you see displacement, horsepower, and weight are all very similar to each other. You can decide, okay, like I'm going to try the model with all three of those, see how well the model performs, and then say, okay, what if I drop out the two that are like, you know, correlated with, you know, horsepower, and just keep horsepower by itself and see how well the model performs there. So that's kind of a way you can kind of like at least like holistically kind of decide, you know, does it make sense for me to keep this feature? But again, in the future, we're going to learn how to use more like a scalp, like a little surgical scalpel, and try to get the exact information. Okay. So you guys, I think we've seen how to do like correlation matrix, right? With pandas, you can just .core. And we can see right here, of course, the diagonals are correlated with each other. But you can see, for example, like I think it looks like horsepower and displacement, very high correlation with each other. Same thing with horsepower and weight. So those are things that like I might want to consider. In high correlation, it's probably something around like, it depends on the situation, but like definitely like anything over like 0.95 would definitely be highly correlated. I'd probably say, you know, 0.85 to 0.9 to, you know, 1.0 would be too correlated. I might consider actually dropping. Okay, does that make sense to people? Cool. All right, and then, you know, simple as that, you just basically drop it. There's another convenient way to look at correlation, because I don't know about you all, but like sometimes numbers just, you know, just starts glazing over, especially when you have many features. Sometimes a heat map is really nice too. So in this case, basically, as we go into the warmer colors, it's higher correlation. So we can see here like displacement, cylinders, horsepower, I'm sorry, displacement, horsepower, and weight are correlated with cylinders here pretty highly. And then the rest of these are like, yeah, there's some correlation in there. I did say we can drop them. What might be the issue about dropping? I kind of described that as using a machete. Like, why wouldn't we want to drop features like that? Or like let's say something's on borderline correlation. You know, what's the disadvantage of dropping it?
Dropping it from your like data or your heat map?
Dropping it from your data, like you're ultimately you're training your model, and so you're feeding it certain features. Why would you not include? What is the disadvantage of excluding that from your model training?
I think adding the features that has same correlation doesn't really add the the model prediction capability. I don't know.
Yeah, so definitely if models have, if some features are correlated, like you're going to double count, right?
Yeah.
But a disadvantage of it is in the same way that like when we talk about the analysis, for most people's assessments, I think that most people decided to drop some information and like null values. By dropping data, and ultimately not including it in our model training, means that the model doesn't know about that information. And maybe there's a little bit of extra like information, within this like this feature, even though it's correlated, strongly. Let's say, for example, weight and, the reason why weight and like, let's say, like horsepower are so closely related is because, maybe it's the engine's most of the weight of the car, or maybe you need to have a bigger engine or a more powerful engine to move the heavier car, right? So there's some kind of correlation there. But, you could maybe reasons like, the weight of the car might just mean like more material, to actually make that car, or like higher premium materials or whatever it is. And that could affect the car. So like, even though correlated, there might be some extra bit of information that it's trying to encompass. Does that make sense? So that's why we want to be careful. Like, we want to consider like, oh, we should get rid of some information or correlated information. But if you get rid of too much, then the model doesn't have as much to work with. It doesn't have as much information to know how well what it should do to predict the outcome for the target. Okay, does that make sense to people? Give me a thumbs up if that made sense. Okay, cool. All right. Any questions about that? Because I think that's a subtle issue, but I think it's an important one to realize, is that the model can really only know how to train well with what it has. Yeah. So cool. So one solution is to drop the feature, right? That might not be the most ideal sometimes. I'll talk about something called PCA in phase 3, where we talk about this. It's a machine learning technique. It's actually an unsupervised learning technique, but that's very common to get rid of this multicollinearity. Another possible way is to do feature engineering, by basically trying to extract information from features by combining together, or using extra information to kind of like tease out this information from a feature that's correlated. Cool. So that's kind of like the next improvement that we want to look at for extending linear regression. And basically, one of those things is just like this confounding factor. Oh, I know. Okay, I'm gonna pick her up for a second, if you guys don't mind. Oh. Say hi. Okay. She likes little seeing videos. She sees all your faces. All right. So, okay. So one of the things we can do to help fix that multicollinearity is with interactions. Right. So basically the idea here is that if we have two features, we kind of assumed in the model, a linear model, that each of those features are in fact independent from each other, right? And so what we want to look at and say, okay, well, what if these features are not independent from each other? What if they interact with each other at some level? So here's a little example. I think this might have actually been taken from the labs, or like the material from the curriculum. But you can imagine that we have something like what country you're in, and then like the weight change is what we want to predict. But the diet right here is like, you have let's take the purple diet, the red diet, and the green diet right here. And maybe they represent, like high carb or low carb or whatever it is, right? And we can see here is that there might actually be a little bit of factor. For example, the USA seems to have less of a weight change, or more of a weight change than the UK. What we also see in New Zealand here is that it looks like, maybe diet B and diet C really don't have a difference in the diet. Okay, so like maybe, for example, I'm trying to make something up on the fly here, but maybe just a cultural thing. Like people in New Zealand, it's like, oh, they don't really have a difference between like, let's say like one of the things like high protein, but maybe most New Zealanders get their high protein from fish already. So the diet doesn't really have an effect in the same way that it would do for other countries. Okay, so does that make sense to people? Like how you can have these two factors, in this case, the country and the diet together can be like a confounding factor because it's interacting together. Okay, cool. All right. So here's a little more of an interaction. So remember how I said that this is from the car data. So remember origin 1, origin 2, origin 3. And I mentioned about how we can make categories, and you can kind of imagine if that they actually are independent from each other, you would expect, in this case, of this horsepower over miles per gallon, you would expect just to move that essentially that linear regression line, right, up and down, right, just kind of like changing the y-intercept essentially, right, because it's that category. Well, this is actually a direct like kind of look at this is that we have, you know, origin 1, origin 2, and origin 3. All right, we have origin 1, origin 2, origin 3, and you can see here if you look closely, that slope is not exact, right? You can, or not exactly the same. You can see there's a little bit of a difference between the two. You guys see that? Yeah. Right. And those lines are basically representing the, if you had a line separate for each origin. Right. Okay. This is Corey, by the way. Hopefully you guys can hear me okay with her trying to chime in. She wants to tell you all about data science. All right. She always says data, but my wife says that she's trying to say data, like dad, but I think she's trying to be like data science. Anyway, so you can see there's this interaction here, or like there's a possible interaction, right? And so it's like, okay, like that might be moderate that you won't really care too much about. Like, okay, there's some interaction on there, but it's not very much. But we can see here in this case, I put like older cars and younger cars. So I kind of grouped them together, being like, oh, like, you know, the older models versus the newer models. And you can see here is that there definitely is a different slope change as we change in horsepower, right? So in that case, it's not simply a category where we're adjusting that linear regression line up and down. There now is actually a real factor where younger cars, as we increase the horsepower, decrease in miles per gallon more quickly than older cars. Does everyone see that pattern right there? Yeah. So this is an example of like how you can identify saying, oh, there actually is an interactive feature here. This also hopefully makes a lot of sense too, right? Like I think if you picture the reason behind like, you know, older cars, younger cars with miles per gallon and horsepower, you can probably get an idea like where that, you know, relationship comes from, right? Just maybe the way the cars are designed. So anyway, that's the kind of the way like you can kind of help identify and see this interaction actually in practice. Yeah. Any questions on that? Okay, so that's kind of identifying it. The way you can kind of include this in your model is actually really easy. So normally we'd have like, and this kind of comes down to polynomial regression, it's very similar, is that instead of having feature x1 and x2, for example, you instead would have not just x1 and x2 by itself, but also x1 times x2. So, and that basically allows that interactive together, or interactive feature together. And you can kind of think of it as being like you're adding a new feature into the model called, you know, interacting term, x1 times x2. And so that allows basically those, your linear model to kind of incorporate that and say, oh, how much strength is this interactive feature together? Okay. For the record is that if you do have an interacting feature, you typically don't want to have, you know, so the next question would be like, why can't I have x1, x2? If I have x1, x2, and x1 times x2, why not just have x1, x2? And the reason why is because maybe there is some information by x1 by itself and x2 by itself, but there's also information about them interacting together. That makes sense? Okay, cool, great. So once you realize that, you can basically make whatever kind of features you want by combining together. And so this actually comes down to, excuse me, just too funny. Is that you have polynomial features that you can say, okay, all right, you're killing me today. Okay, you can have this x1, x2, like x3 features and all that stuff. You can have x1 and x2, x2 and x3, all these features, right? You can also have, in some ways, features that interact with themselves, which sounds kind of weird, but basically that means is like instead of having a linear relationship, we actually have something that's a little more complex, and that's what polynomial really is. And people talk about polynomial regression as if it's this really crazy new thing. All polynomial regression really is linear regression, but now you also include one of your features. So like remember linear regression here, we have our weights, and this gets to use W, but remember back when we use beta. So we have our weights, our coefficients for each feature, all the way to the end features, right? And just multiply it by some value. Well, if you imagine like xn here not being a single feature, but being like, you know, a feature times itself or a feature times another feature, it's really just linear regression. It's just that you just defined a new feature. And that's what polynomial regression looks like. So you can see here in this case, I'm using essentially just literally one feature in this case, just x. And you can see here I go like not just x, but x squared all the way to like x to the power of n, right? And you can see is that we basically, it's the same exact thing. It's just that x to the power of n is just the feature, if that makes sense. Okay. So with that, then we can actually take data like this that would not normally be would not typically be linearly related, and actually use something like a polynomial. So in this case, on this very first graph with the line, we see a quadratic, right? So you can imagine like if you have something like an x plus x squared, right? So kind of a typical form of a quadratic. Yeah, I'm showing off. And this graph right here, you can actually have a polynomial regression. So this is actually like maybe like something to the power of 6. So we have x plus x squared plus x to the power of 3 plus x to the power of 4 plus x to the power of 5 plus x to the power of 6. And you can see like of these two regressions, which one's closer on the data points? The first one, the top one, or the bottom one?
Bottom?
Yeah, bottom does get closer. What might be the issue with the bottom one? Even though
It's not easy to predict.
yeah, it's a little too it forms like, I think when you say not easy to predict, can you go into a little more details, Nick?
I guess it's not like a natural function. It's like quadratic even, or not quadratic. It's whatever to the fourth power would be.
Yeah, there's a lot of humps and stuff. It's more
Yeah.
complex for sure, right? And in a lot of ways, that's what we call overfitting. Basically, it's so complex that it technically fits better, but you can imagine now if we had a new data point that wasn't quite on that line, like if we had a data point that was closer to like right here, maybe there's just one example, this line might actually do better overall when it comes up with new data that's kind of fluctuates around. The extreme of this would be like literally a model that has like connect the dots, right? It would be like literally every time there's a dot, it tries to connect it directly on there, which you can probably guess is not really a good accurate model because obviously, you know, you're not going to find an exact dot on that line. Okay. Does that make sense to people? Okay, cool. So that's the general kind of idea. So you want to be careful about like how much complexity you actually add in. Now I did this with one variable. In reality, what this would be is that if you imagine, this is like really complex, like looking math right here, but you can kind of imagine this is that each of these like capital sigmas here is summing over basically, this is one feature, bless you, little x1, x2, right? So like you can say like, this is x1, so some feature, but then using every possible polynomial up to the power of n, okay? And then doing the same thing for x2, right? And every possible like x1, x2 to the power of 1, x2 to the power of 2, and so on. And basically you have basically all of these different polynomial features. So like the general equation would look like this. So if you ever see this like in some kind of text or some kind of research, just kind of know that this is literally the same thing here. Okay, makes sense? Hopefully that doesn't look too scary. Okay, so there is no limit to the polynomial tree. I mean, technically there's a limit in the sense that like you can only put so much in the computer, but really you could raise it to the power of like 100, right? And that means if you had like, let's say, you know, 10 features and you have, you're using 100 powers, right? Like n to the power, like n is equal to 100. So you have x to the first, x to the second, x to the third, all the way to x to the 100th for each feature. You'd have not 10 features anymore, but 10 times 100 features. So you went from 10 features all the way to 10,000 features, or not 10,000, 1,000 features. Would you think about that? Like that's a pretty big jump, right, in complexity. So you always want to be careful about that because you will technically get better results with your training data, right? Your R-squared value will get very close. And that's why we use validation methods, right? Cross-validation to ensure that like, hey, if it's getting complex, it's not going to do well on data it's never seen before, right? That's also with R-squared, right? So what would happen if I added like that scenario where I had 10 features originally, make a model, get an R-squared value. And then I do that with polynomials with up to 100, the power to 100, right? What would we expect R-squared? Would R-squared get worse or better for the training data?
Better.
Better.
That's right, it would get better, right? You would see it better. And that's when people say like, wow, I got such an amazing model. This is awesome. How would you make sure like Because you would see that, you're like, oh, cool. How would you make sure that you know if your model actually is better?
You mean
Mhm.
you mean better for the training data set only, or like in general?
I can say like in general.
I mean,
They adjusted R squared, right?
Adjusted R squared would be one, right? Because now adjusted R squared basically is trying to keep in fact that if you have more features, it's more complex. So you should like, you basically, you don't get a free pass, right? Adjusted R squared says, hey, like you're using more features, so of course you can get better R squared. Let's bump that score down essentially. There's another thing we could do too, which we kind of talked about last time, is making sure we do validation, right? So we use new data that we haven't used on the model training itself and see how well that performs. And that will tell you pretty quickly if you're overfitting, because you'll see that score go significantly lower. What do we expect? Let's say a model's not overfitting, right? So it's actually like doing pretty decently. Like we actually know like in the end, that's actually a good, decent model. Would you expect the R squared value on the validation data? Would you expect the R squared value to be better, the same, or worse than the R squared for the training data?
it would be same or little less.
Yeah, in general, you'd probably be maybe about the same, but more than likely a little bit less, right? And that makes sense because you don't have those examples yet, but hopefully it's not too much lower than what you originally had. Okay, cool. All right, any questions? Not from you. No, sound pretty good? Okay, cool. So hopefully that all makes sense now, because I will tell you is that especially with scikit-learn, it's really easy to add these extra features. Like literally it could take like a couple lines of code, but understanding the concept of it will help you know when you should use it, or file it back or whatever. Okay, cool. All right, so really now you kind of know pretty much everything that's talked about from topic 18, 19, and 20. Okay, so at this point, it's kind of good to kind of go through an example of what this might look like in walking through a full linear regression. Okay, like a little example. So let me go ahead and pull up one of those notebooks. Okay, so, oh, sorry, I'm on the wrong machine learning. And then linear regression, and then the walkthrough. Okay. So I believe this is the one I just want to double check. I'm pretty sure. Okay. Cool. All right. So what we can do now is actually walk through this whole, like what this process would look like. And this is actually pretty close to what you might do in the actual project. Obviously, you're going to take a lot more time than just like, a few quick minutes, but I just wanted to show you a little bit like what this might look like. So let's get our libraries loaded. And then one thing to remember, I actually don't know where this appears in the curriculum. It might actually not even be in the curriculum right now, might actually be in phase 3, but something to keep in mind. And if someone's seen it before, let me know. It's the thing.
It is in the curriculum.
It is in there. Perfect. Thank you. The data science life cycle. This is actually a really good thing to kind of consider, because I think I would say that this project that you have for phase 2 is closer to a full data science project in the real world than the phase 1 project. Not that the phase 1 project wasn't like really useful in analysis, but I would say like a total project would be like the next steps would be like, okay, can we make predictions and stuff, depending on what the work is. So in this case, like the first part to understanding is like, okay, understand the business understanding, understand what the business needs, what the clients need. And then, actually looking at the data saying, okay, like, do we understand this data, which ends up being about like cleaning, exploration, right? So kind of like a little bit of cleaning, a little bit of exploration. And then we have data preparation, which really is just about like cleaning it and stuff like this, but also it's feature engineering. It's developing those features. So, do we need interacting terms, investigating the data and seeing what makes sense and maybe creating new features that weren't originally in the data by itself, okay? Then that final part, we have a modeling, right? And so you'll see right here, is that there's a couple errors going back and forth. And for the record, I think that almost all of these like steps can be done like back and forth. But data preparation modeling, you'll see there's a back and forth error there, because what will happen, we'll try something out with the data, we'll do a model, and we basically evaluate that and say, ooh, like I think we could do better. And then you go back to feature engineering, create some new ideas of how to combine the features, and then model again and evaluate. So it's an iterative process where you go back and forth. Okay. But after that kind of idea, we have our evaluation, and we have hopefully like our final evaluation. Say, hey, does this work well? This is where you kind of see a little bit like an arrow going back and forth to business understanding or deployment. And really, you can think of like deployment as being like the final steps. Like, okay, we have a good model. How do we get our clients? How is it useful to other people who are not data scientists? And that's kind of like the next step. We won't be doing that really too much in this project, but you can kind of think of what the next steps might be. It's like, okay, how can we use this model to make predictions that are useful for our clients? Okay, cool. So we're really going to focus right now on this stuff right here, which is going to be more about the modeling and evaluation, because that's kind of like the newest stuff, and a little bit of like the feature engineering. So this right here is usually defined as CRISP-DM. So it's like this cross-industry standard process for data mining, which is super long. But CRISP-DM is kind of like, for most data scientists, if you say CRISP-DM, they know what you're talking about. They know this, it's this process. A similar one that I think is a little less common, but I do hear people say it's awesome, pronounced like almost like, something's awesome, like totally awesome, which is obtain, scrub, explore, model, interpret. I don't like that one as much, to be quite honest, because it just seems like they're very like strict, like, oh, you obtain the data, you scrub the data, you explore the data, you model and interpret. And like, it just feels very like, that's not the process. Like, it's very much like it's a little bit of a messy cycle here. Okay, but for the record, that's what that would look like. Okay, cool. Any questions on that? Okay, cool. All right, so let's actually do some of the stuff. So first, data preparation. So we're just going to get some data in here. In this case, I'm using some Kaggle data. It's like New York's, I think it's like Airbnb data, if I remember this right. So let's just go ahead and load that in there. And then, I'll do some investigation, check out, what are the different features. I have ID, host name. So probably ID is not going to matter too much other than just identifying which listing with which target. But we have some other information too, like, the location with longitude, latitude, what kind of room it is, which can make sense. Like, oh, if it's a really big, if it's like a private room versus like an entire home, that's going to be very different, and then you can see also like a room minimum nights, stayed, number of reviews, and all that good stuff. And then ending up here, which is our target, is the price. It's like, how much is it going to rent per night? So that's kind of like the idea here. Okay. So yeah, and again, we can explore a little bit more. In this case, there's a little bit of missing values and stuff like that. So something to consider when we're actually putting this in, because if it's missing values, we can't predict off missing, right? At least not directly. We have to decide, do we keep those data points to encourage, like, to help build up our model? Or, do we ignore not the data points, but the actual columns? Say, hey, you know what, last review is just not useful for us. Or do we try to fill in, some information about last review, because we have a good idea of what last review should be for this missing values. Okay, everyone follow me so far? Cool. All right, so the first thing to do is actually get that target away from the rest of the data. So we have our features, which usually is signaled with capital X. And then we have Y here, which is basically just that last column, which is price. Okay, so I got that guy. It's like, okay, I got my data. Now the next step you should do before going really any further than this is really like looking at splitting up your data into a train and test sets. And you can think of this test set not like the final test set, but more like your personal test set, what we call a holdout. The reason why we call it holdout is because we're not supposed to like really be looking at it, touching it at all. Okay. You should ideally do this before you get really into the weeds of the data exploration. And the reason why is that you don't want to incorporate too much of that information from your holdout set into how you train, because then you end up just you start incorporating that stuff where in reality, when you deploy, you're not going to know what data comes in until it's in, right? And you made a prediction already. So you're basically trying to simulate that. Okay. Everyone follow me on that? Yeah, thumbs up if that made sense. Cool. All right. You can see I still hear me with her just kind of babbling away, right?
Some of the data, some of the object type data, shouldn't we convert them into a category or something?
Yeah, we'll have to investigate that a little bit closer. So like we can see object, obviously, we have more of like a listing here. I think one of these ones actually has, what's the other one? Last review. Last review here, you can see, it looks like it should be a date, but it's just getting an object right here. So we could possibly convert that to a date time or extract things. Maybe all we care about is not the year. Maybe we all care about is like the month, but we don't care about the day or something like that. So we could extract that out saying, okay, instead of last review, which would be the actual date, maybe we extract the year separately and the month separately and the date separate, or like the date of the date separately. Okay. Yeah, but good. That's good to go look and check it out. All right, so just to show you again, now we have all the features and then there should not be any target. For the record, if you accidentally keep X, like let's say you just make a copy and you actually do keep that last, the target as part of one of your features, your model's going to do really, really well because I already know is basically the answer. So kind of be careful of that. So that does happen sometimes. And that's what we call data leakage. Okay, so this is where like you would do data exploration. I'm not going to go into that just because like I want to show you how to build this model. But this would be like the next step that you would go into. Okay. Data cleaning, kind of similar thing. I'm not going to go far into this. I don't really want to like spend a whole bunch of time on that, but I think you guys can figure out, you know, it's similar to your analysis is you want to figure out what's important, you know, and how you can combine these things together. Okay. So assuming I already got like figured out what features I need to do and all that stuff, what I want to do now is just like, okay, like let me just go ahead, like take out the features that I don't need anymore. So in this case, it's actually a really good idea to actually create a function that will do this for you. So in this case, like I am passing in like my data frame, my features data frame. It could also be just a NumPy array. But basically I'm just going to keep only certain features in here. So in this case, this is a very, very bare bones, you know, example. But in this case, I'm keeping all the features except for the first one, right? So that would be kind of like similar. It's like, okay, I don't need the ID as one of my features. It's not going to be helpful for me. So in that case, I'm just getting rid of the ID. And what's nice is that you can build this up as you kind of do your feature engineering and stuff and kind of change this function. So Mom, you had a question, I think.
Yeah, isn't it too early to split the data at this step? Because since we are doing cleaning and some feature engineering, because then you have to do this all this feature engineering for the two data sets separately.
You're right. Yeah, you will have to do it separately. And I know you're saying like like, oh, like, you know, that seems more work, and that's why getting used to having a function that says, okay, these are the things that you should do if you see that, like, you know, for example, oh, remove this value, or say, oh, we should, you know, scale this value or replace, you know, with, let's say replace missing values with 0. You would do that separately away from the test set, and you would basically build out your functions to do that for you. So then all you have to do is pass this function or something like this onto, instead of X train, onto X test. And then,
right. So instead of doing that, like how about like doing all this step first and then splitting the data at the end before the training the model? Like, will that change the result or like?
Yeah, so it can be, it'll definitely change the result if you like use that method, because let's say, for example, you scale everything, what's it called? You scale everything down to like the maximum value, right? So everything has to be the maximum value. So what, you know, you use that, you figure out that feature engineering part, and you reduce all those values down to 1 for the maximum. Well, the problem is that if you use that test set, you now have a new maximum in there, and that could affect basically how your model will perform. Basically, it's like it knows some information about what you'll eventually test on. And this is what we call about data leakage. It's a little subtle because it doesn't seem like it would be a big deal, but that could be the thing that basically, like what we are trying to do essentially is simulate a real life situation where we don't know the new data coming in. Okay, does that make sense?
Yeah.
Yeah. But yeah, there's some nice things that we can kind of walk through. One of them is called a pipeline. And sklearn is actually really great with pipelines. I know it's not in the curriculum for this phase. You do see a lot more pipelines in phase 3, but I do think like keep that in mind, like pipelines just in your radar Even if you don't use them this time, I think they're super useful. Okay. Cool. But for now, at least keeping like a function, I think is really helpful. Okay. So, all right. So then I basically, in this case, I'm just dropping that one feature. I could probably drop out more, or, this could also be, I can make a function that says, replace missing values, and actually say like, okay, if it's a missing value for this column, replace it with this value, right? And then so on. Okay. So cool. In this case, I ended up keeping 11 features. There's 25,000 different data points to actually train my model with. Okay. Anyone follow me? Any questions? Oh, pretty good. Okay. So then let's go and start working with these numerical features. So in this case, I'm just going to look at those features that I have, and note that I have X train features now. I'm renaming it so that way I still have the original X train data. So if I want to, I can kind of change things up again. I'm making a new copy, right? So let's check out those columns. And in this case, I've decided that those columns, that some of them just aren't, useful. Like they're not numerical, at least for what I have right now. So like room type, for example, like, can't really use room type. Like it's not numerical. So maybe I want to remove that, as well as like maybe like hosting ID or like host name. Like host name might not really be super useful. Maybe there's some stuff we could extract that out in the future, but at least initially I'm like, I just want numerical features. Okay. So I think I don't even have room type in here. I think I'm going to keep that. So again, I'm creating a function here that basically will, oh, these are room, that's why. These are columns to keep. Okay, so basically I'm going to take in my data frame, which is going to be X train features, and only keep those columns. Okay. So I run this guy, and now I can actually apply this, get numerical features. And now I have just the features that I think are going to be useful in this case, are not useful, but like in this case are numerical. If there were like this might be something similar where you have a category groups. If I had more time, I would go through and say, okay, I want to keep these features, but make these into categories. And I would do something similar where I'd make new categories and then add that onto my overall feature list. Okay. Does that make sense to people? Okay, cool. All right. Now we get to missing values. So this is where I talked about, like, you have to decide what you want to do with missing values. So here again, create a data frame, or I'm taking in that data here and actually doing something here. And so in this case, I'm actually going to find the medians for each column. And remember, I'm not going to just fill it with zeros. I'm going to actually find what is the median for those features and then fill it in if it's missing in this case. So you can see here as those fill NA values, that's what's going on here. And that column right here is just basically representing the column in this data frame. So for example, we see reviews per month. Excuse me. I'm going to find the median for this data and fill it in with that. Okay. So one thing to note though, is you'll see that I'm passing in my data frame and train data frame. And the reason why is kind of looking ahead and a little bit like what Simon was saying, like you have to do this twice, right? Like once for the train and one for the test. Well, in the test one, I don't want to take my test data, right, and find the median there. What I want to do is use the median that I've already found. Otherwise, I'm using that median value. It's encompassing some information about the testing data frame. Okay, so that's actually why in this case, I'm actually passing in the training data frame explicitly saying, use this data to find the medians and then replace the values on whatever this data frame is. In this round, it's going to be literally the same data frame, but later on, this will be like, X tests. Okay, does that make sense to people? Okay, so again, I'm trying to like make this so it's a little bit easier for me to use in the end. Okay, and again, this is the thing I work off. So as I'm exploring and figuring out things, I'll add to this function and like recreate this function and make this function, more complex and stuff like that. Okay, cool. So now I have this data, and you can see here in this case, I have missing data for reviews per month. I can see reviews per month, 0.09. Okay, or it's not 0.0, 0.73. Looks like that was the median. Okay, and then we can see missing values. We should have none of them are null. Cool, and you can see again, we're all numerical. Everyone follow me on that? I'm pretty good. Okay. Finally, we have categorical data, which again, I kind of said like if we had more time, we would do this, but I'm not going to go into this right now. And then finalizing my features and labels. So that's basically, I'm just explicitly making sure that I call my final thing features. That way I don't have to pass in X train numerics filled or something like that and then put that in my model. I'm just calling it features. That way I can just pass that. I can just run dot fit features comma labels. Okay, does that make sense to people? Okay, cool. So get that. For the record, you probably aren't going to change the labels at the end. You're probably going to, and I call it labels, but you should think of it targets. You're probably not going to do that because you'd want to have your model predict well on that. Okay, so let's actually model. So like after doing all that work, and which that right there is the thing that takes the most time. This is really easy, right? We saw this before. We import, in this case, I'm using sklearn's linear regression. My model is equal to linear regression, and then my model.fit with the features labels. Okay, and boom, I trained my model to make it predictions, right? So now the next part is actually evaluating how well did my model actually do, right? And so we talked about like finding the coefficients and intercepts. So I think I showed you guys that last time, like how we could look at those coefficients for each feature, especially if we scaled it. In this case, I didn't scale anything, but if I scaled it, I could read off those coefficients to like get an interpretation of like what I think is what the model finds the most like useful and stuff. Okay. So in this case right here, I'm just basically making it so it's a little bit easier for us to read. So I made a little data frame here, and you can see here the host ID. This was the coefficient for host ID, latitude, longitude, and you can see again we didn't scale it, so those values are very different from each other. But that would be the idea of the coefficients. Okay, make sense? All right. So okay, cool. Like we got our stuff. What do we do with this information? Does someone have a question? No, maybe it hurts. No. Okay. All right, so what we'd like to see is actually we can make predictions with the p-value. This is actually a good idea to check out. So one kind of thing you can do if you're like, man, I don't want to do this. I don't want to recalculate the p-value for each of these things. Like, it's just like, I don't want to write that function. What you can do is literally just run OLS on top of it, because OLS and the data that you have should technically work together. And so you can double check that. And the way you can double check that it's actually the same model is looking at the coefficients. So those coefficients should be about the same. Okay, so that would give you at least that p-value in there. Okay, so then we want to see, okay, we got this. Let's actually check out how well this model did. So this is where I talked about k-fold validation last time. I don't think I showed you all how you actually like program that, right? I don't think so, right? So this is actually how you would like run this. So basically, sklearn has this cross-validation score. And what it's going to do is going to take in my model. It's going to take in the features and the labels. So remember, these are my training data, right? And then in this case, I'm going to say CV. That's basically how many folds you have, right? So how many cross validations you have. In this case, I have 10. Usually, I think it's, again, I think it's in the literature, it's like 5 or 8 or 10. I think that was kind of like, those are the sweet spots. More or less of that doesn't seem to be very helpful. And note that I have the scoring here. I have the negative mean squared error. Note that the scoring, usually, do we remember what mean squared error is? Give me a thumbs up if we remember what that means. Okay, good. For the record, like in case anyone forgot and didn't show the thumbs, mean squared error basically is looking at the residuals and taking the that squared error and then saying what's the average error, essentially, the mean. Right? So the reason why they're passing in negative mean squared here is because this actually this scoring system has to mean that when the model is doing better, it should be a higher score. So the problem is like if we had a mean squared error of 1,000 versus a mean squared error of 10, 10 is actually better, but 10 is like, numerically lower. So we basically flip that. So it's a -10 and then -1,000, right? So then that way we can actually have something else as it's getting better, the score gets better. Okay. So just kind of know there's a little bit of that. And if we run this now, we actually, I also put in the, the root mean squared error scores. I'm basically just taking those scores and just doing the negative so we can actually read the root mean squared versus the negative. It's a little bit easier for us to recognize. If we run this now, you can actually see this is actually cross-validation. You'll see that in this case, 10 different scores for the root mean squared error. And then I also did the mean and then also the standard deviation. And so you're like, okay, like what does that mean, Victor? Like what's going on? So what this is right here, this is basically after each model was, like this model was trained with the features and the labels after that fold and then evaluated with that, one fold, right? And this is the score for that evaluation. So this is, it technically was a negative RMSE, right? But I'm actually getting, I made it positive, right? So basically our root mean squared error is about 245 for that first fold. The next one, it looks like it did a little bit better, or yeah, did better, 164. 149, 256. So you can see a little bit like what that fluctuation is. Like sometimes the model does pretty well. Sometimes the model does a little bit worse, right? On average, it did about 205, right? Was the average, and the standard deviation of 39. And in this case, I can actually use the root mean squared error on the scale of the original target. So remember, the target was about what the price is per night. Basically, this is telling me how many dollars. Basically, it predicts on average the error is about $205. Like basically, like how much error you have, which in this case is probably really bad, right? Because like most rooms are probably like maybe at the range of like $400 a night. Like, you know, maybe there's some more extreme ones. So this model is not that great, which kind of makes sense. Like we didn't take any time in feature engineering at all. So hopefully that makes sense. Okay, give me a thumbs up if that made sense of like how I'm interpreting this root mean squared error. Okay, so if you do that too with your model, you should know what the scale is, because people usually will say to me, I have an RMSE of this value. Is that good? And I'm like, depends on your target. If your target's in the hundreds of thousands and you have 205, that's amazing. If your scale is like on the hundreds, like, you know, most of your values are like, you know, 100, 200, 300, and you get a RMSE of 205, that's not that great. Okay. And then note that, again, I did the standard deviation. That's just showing me how much it fluctuates every time I trained it. So again, that's a little bit higher than I would want, right? I probably want something a little bit smaller. I'd want my models to do really well generalizing. Okay, cool.
I had a quick question about what the reason that you did the negative scores, because later on you said that the 164 performed better than the 245. Is that correct?
That's right.
So what would have happened had you not used the negative score in the cell above?
This one right here? Like you're saying if I didn't use negative on this scoring?
Yeah.
Yeah, let's try that out. I actually don't really know what ends up happening. Oh, that's not a key that's available. The reason why that isn't available is because these are predefined. So you could actually define your own scoring system for the record for sklearn. But basically that's just to say, how do I say this? The sklearn's cross-validation score knows it's looking for a score, and by definition, the score should be, if the value is higher, it should be a better model. So I'm trying to think exactly, the reason why you use this, so in this case, if we use a different scoring system, it wouldn't really matter other than like, you know, it would give us different values. The reason why we use this scoring is that you can actually pull from cross-validation here. You can pull individual, like for example, I see, that first model did 245 for the RMSE. And you're like, well, what was that model? What were the coefficients? You can actually pull that out for the model and like how well it performed. I don't know if I show that example here, but if I can type, see if I can show you real quick. I have to think. I have to think about how to pull that out. I think it's. But anyway, you should be able to actually pull out the specifics of each of those models essentially. I think if I could look at the documentation. Hi. I'm sorry, I'm wrong on this. That you can actually pull out more than just the scores. I'm thinking of something else. I'm thinking of grid search. Yeah, I'm trying to think a little bit like why, like I don't think it actually, when I think about this now, no, I think you would have to make sure the scoring does make sense, because that's how it knows how if the model's doing better or not. So like as it's training, it's figuring out what's the best way to make this model. So I think you do have, no. Oh, you got me into like a weird thought right now, Safe. But I think in this case is that it wouldn't affect the model training for validation, the cross-validation score. It'll just return a different value. I guess I could prove this if I actually look at.
We can come back to that later, or like over DM or officer.
Yeah, absolutely. Yeah. Anyway, you could play around with it and kind of see all that stuff. Okay. But you can see here, again, these are results, and we can see what the actual target was. the standard deviation for the target for y looks like 221. So yeah, plus or minus, like you can imagine that scores that varied from 221 on the standard deviation. So that's not bad, but I think in general, like if you think about that, it's not a great, like it doesn't seem that great. It probably could be a little bit smaller if you wanted a good model. Okay. Cool. All right, let me move on then to the next part. So it's like, okay, cool. Like we did just our training data. Sorry, they're like talking to each other. Let's see here. We already did it with all our training data, right? And now we want to do is like, hey, we had our test data. Like, let's actually, like, let's see how well that performs, right? So the good thing is that we actually have these functions that we made earlier. Let me see if I can put it down. We actually have these functions that we made earlier, right? And basically what I can do here is pass an X test. So I'm actually like nesting like 3 functions together, but you could like technically do one by each one. So the first thing, the needed features from X tests, get the numerical features from X tests. It's the same order and everything. And then this final one is fill null values. That takes whatever is left over now, and then using the X train numerics to fill in those null values. So remember that I noted about that function that has 2 parameters. So this is the feature set, the test features, or the features from the test set. I'm passing that in, but then making sure I fill in the values using the training data. Does that make sense to people? Okay, see nods. Cool. So once I have that, I now have my X test file. So this is kind of like my final shape, and it should be 11 features, I think, if we saw that before. Oh, it's 8 features. Oh, that's what it is. Okay. So we have 8 features now in total. We have this many data points. And now what we want to see is, okay, my model dot predict, which I don't think we've seen before. But now that my model's been fitted and everything like that, it's like set in stone. It knows what the coefficients it should use and everything like that. And it's going to use those coefficients, the model, and use the test features here to make a y hat, our predictions from things it's never seen before. So I run this now. This should be the same, like same number of points, but only one feature, right? Basically, not one feature, but like one column. That's what this is saying, because it's just whatever the predicted value is. So to actually see how well it performed, we actually have the real values called y test here, and we can get those residuals where we take y hat minus y test, right? And we can see here, if I see this as a list, basically this is showing us right here, and these are just the IDs, that's why it's on the left here, but these are just showing us basically it was off by $43. So in this case, y hat was $43 more than y test. In this case, it was $114 too low, right? So this is the way we can kind of like evaluate and see how our model, how our data looks. I think we can actually do, let's figure this real quick. Oh, we had some really extreme values apparently. But you can basically take the eval, you can kind of check out what you do dot this plot. So you can see we have some really extreme values. So somewhere down the line, it did really badly. But you can see here is that for the most part, it's kind of getting a little bit more on the lower side than the higher side. So we can kind of evaluate that and say, okay, what can we do to change and like reiterate and change our model? Okay, does that make sense to people? Thumbs up if that made sense. Yeah. Okay, cool. All right. Okay, so let's say we get our model, like, all right, I feel pretty good about this model. I want to make sure I don't have to retrain it all over again, like run the code. You can actually save your models. And so you can actually take your model and save it as a file. And this is actually can be done with 2 ways. One is pickle. And you can kind of think of like making a pickle jar and you're pickling your model for like later use. So what we just do here is this module called pickle. We go pickle.dump, and then my model, so like just what we trained, right? It's already trained and fitted. And just I'm saving it to a file. And that's what this notation is. This WB basically is writing bytes. So it's a little bit different from writing a text file. So if I tried opening up this .pickle file, it will look like, you know, I can't really like read it like on my computer, but it can be read later on. So I create this file here. And if I go to here, you can see now I have my model simple SOL solution.pickle, right? And then I can actually take that file and read it in. Should be able to read it in. What just happened? sorry, maybe oh, I see what happened. It's a different name. So now I can read that model in there. And then I can actually take that model and actually do something with it. So I have my coefficients here. Yeah. Cool, makes sense. All right. Another method you could do, similar, it's just job lid, same idea. All right, question I saw. I think I heard someone on mute.
Yeah, can you retrain on top of that, say on that model? Like,
yeah, so you mean like iterate on top of this? For linear regression, that doesn't make as much sense just because essentially the linear model is determined purely by the data. For other machine learning algorithms that you guys will learn later on, sometimes you can save the model and then take that model and train even more on top of it. So this is really true for iterative models like gradient boosting or deep learning. You can basically take that model's like checkpoint and not retrain it, but like train on top and get better and better. But for linear regression, it doesn't really make as much sense because essentially the way sklearn does linear regression, though you can do different ways to force it to do that. It basically is a deterministic, like once you have the data, this is the best solution for the data. So you could technically do it, like, let's say I did like dot fit, right? And then pass in new data. I could do that, but it's like the same thing as being just like make a new linear regression, you know, like new model equals linear regression and then dot fit. So it wouldn't really change anything. That makes sense? Okay, cool. All right, any other questions? Good, Willa.
Is that notebook in your repo?
Mm-hmm.
Okay. Which section?
Yeah. It's under machine learning and then linear regression.
Linear regression. Okay. Thank you.
No problem. Okay, cool. Yeah, so that's kind of, I showed you like very quickly like what that process looks like. So the next part I'll show is actually what we'll go through the Kaggle competition and show you like what that process might look like, and hopefully we can kind of like do a submission all together. But before I do that, I just wanted to ask, is there any other last like burning questions about linear regression or anything we talked about over these past couple of days? How are we feeling overall? I'm feeling pretty good about this. Like thumbs up, or like I get the idea of it. I think we can do all right. Systems sideways, yeah, that's good. I expect you guys right here because you just watched me do a bunch of stuff. So I'm sure like once you start doing it too, you'll see like where it doesn't work or you know what you need to do. But the general process, hopefully, especially this this linear regression walkthrough, like Bula asked, like where it is. If you go on the repo, you can like at least look at this and kind of like play around with how to make this work. Okay. Cool. So let me go ahead. I'll continue sharing. And let's hear. So we're going to talk about the Kaggle competition. So real quick, thumbs up. Who's made a Kaggle account? Yeah. Awesome. All right. This is where I tell you all is that like this Kaggle competition is optional, right? It's not going to be graded. It's not going to be like, you know, a factor in, you know, anything, right? It's more for a practice and a little bit fun too. So we're going to walk through a little bit. I'm going to show you a little bit of how to make a submission. You guys can maybe do this too as you're like watching me do this as well. And I'm going to show you some tools of Kaggle, and then, you know, hopefully by the end of today, and I would say like the end of today being like, you can just make a dummy submission and be like, let me just try a submission out. We also have the option of making teams too. So, but I'm not gonna assign any teams. But you're welcome to also just do it by yourself too, especially if you're just like, you know what, I know I'm gonna be super busy, or you know, I just, you know, just don't have the time right now. It's perfectly fine to just do an individual, and you can still talk with each other even if you're individuals. Okay.